Hello everyone, welcome you all in a video lecture series related to heat and mass transfer. Today we are dealing with convection chapter. In this lecture we are going to learn the empirical correlations for free convection and the combination of free and forced convection. In the today's lecture, our first point is empirical correlations for free convection. In the previous lecture, we have seen the dimensional analysis application to a natural convection, and we will get the relation as nu is equal to function of gr and pr, where nu is nothing but Nusselt number, gr is the Grashoff's number, pr is the Prandtl number, and we can interpret this functionality equation as nu is equal to c multiplied by gr raised to a multiplied by pr raised to b, where the c, a, b are the constant and can be determined experimentally. Now, in a free convection, whatever the correlations are there, that correlations are surrounding to this relation only. That is nothing but nu is equal to c multiplied by gr raised to a multiplied by pr raised to b, and this constant c, a, b varying according to geometry and the flow condition. In several cases, the above equation simplifies to the form nu is equal to c multiplied by into bracket gr multiplied by pr raised to m, where c and m are the constant. So here we can say that new dimensionless group is formed, that is nothing but gr multiplied by pr. Now this dimensionless group is called as a Rayleigh number. So it is denoted by capital R small a is equal to gr multiplied by pr. That is nothing but Rayleigh number is the product of Grashoff's number and Prandtl number. So in a natural convection, this Rayleigh number suggests us that which type of correlation we should use for the flow type. That is nothing but the Rayleigh number suggests us that whether the flow is laminar flow or the turbulent flow. The following dimensionless numbers apply for the usual free convection problems. So in the dimensional analysis, we come to know that the three important dimensionless numbers included in the correlation, that is nothing but Nusselt number, Grashoff's number and the Prandtl number. So these three dimensionless numbers are more important in the natural convection. So we have seen the Nusselt number, that is nothing but nu is equal to hl divided by k, where this h is heat transfer coefficient, L is the characteristic length and the k is the thermal conductivity. Also we have seen the significance of a Nusselt number. It signifies that the enhancement of heat transfer because of the convection. If Nusselt number is equal to 1, then the heat transfer happening because of the conduction only. And if the Nusselt number is greater than 1, then the heat transfer by convection dominating over the heat transfer by conduction. Then second number is nothing but a Grashoff's number. So this Grashoff's number specifically used for the convection purpose, for the natural convection purpose. So here this Grashoff's number can be denoted as a gr is equal to L cube beta multiplied by g multiplied by delta t divided by nu square, where L is the characteristic length, beta is the coefficient of volumetric expansion, g is the acceleration due to gravity, delta t is the temperature difference between the surface and the fluid, where the nu is the kinematic viscosity. Now this Grashoff's number specifically used for the convection purpose, and its significance is same as like of a Reynolds number in case of a forced convection. In case of a forced convection, as we increase the Reynolds number of a flow, then the effectiveness of a forced convection also increases. So in same manner, in a natural convection, if the Grashoff's number value goes on increases, then the effectiveness of natural convection also goes on increasing. Then we have seen the Prandtl number. So the Prandtl number is equal to mu Cp divided by K. It deals with the thermal boundary layer and the velocity boundary layer. Now, if the Prandtl number is equal to 1, then we can say that the thermal boundary layer line and the velocity boundary layer lines are collapsed on each other, so that the diffusion of heat transfer equal to the diffusion of heat equal to the diffusion of momentum. If the Prandtl number is greater than 1, then we can say that the momentum diffusion will take more time than the heat diffusion. If Prandtl number less than 1, then we can say that momentum diffusion does faster than the heat diffusion. Then here we are going to see the this particular empirical relations for the vertical plate and cylinder. So the commonly used correlations are, first relation is for the laminar flow. Now the flow is considered to be laminar if the Grashoff's number multiplication by Prandtl number, that is nothing but Rayleigh's number, is in between 10 raised to 4 to 10 raised to 9. So at that time the flow becomes the laminar flow. So we can say that in that case the average Nusselt number can be written as Nu suffix L bar, that is nothing but average Nusselt number, is equal to 0.59 multiply into bracket gr multiplied by pr raised to 1 by 4. Now if this Rayleigh's number is in between 10 raised to 9 to the 10 raised to 12, then we can say that the flow is a turbulent flow. So in that case we have to use the correlation for average Nusselt number is equal to 0.10 multiplied by Grashoff's number multiplied by Prandtl number raised to 1 by 3. Now here we have to remember that to calculate the values of Grashoff's number and Prandtl number, we required the fluid properties, and this fluid property should be taken from the tables. Okay, so this fluid properties should be considered at a mean fluid temperature, or we can say that mean film temperature. So mean film temperature is nothing but average temperature of surface and a fluid divided by 2. That is nothing but Ts plus T naught divided by 2. That is nothing but mean film temperature. Now for the vertical plate and cylinder, Churchill and Chu also recommended the equation. So according to Churchill, the average Nusselt number can be written as 0.68 plus 0.67 into bracket gr multiplied by pr raised to 1 by 4 divided by, in a square bracket, 1 plus in a bracket 0.492 divided by pr raised bracket complete raised to 9 by 16 square bracket complete raised to 4 by 9. Now this equation can be used when the Rayleigh's number is less than 10 raised to 9. That is nothing but product of Grashoff's number and Prandtl number less than 10 raised to 9. If this product is greater than 9, then we have to use the correlation. The average Nusselt number is equal to 0. In a square bracket 0.825 plus 0.387 multiplied by Grashoff's number multiplied by Prandtl number raised to 1 by 4 divided by, in a small square bracket, 1 plus in a bracket 0.492 divided by Prandtl number small bracket complete raised to 9 divided by 16 square bracket small square bracket complete raised to 8 by 27 and big square bracket complete raised to 2. So it will be used when the product of Grashoff's number, Prandtl number, that is nothing but Rayleigh number, is greater than 10 raised to 9. Now the empirical relations for the horizontal plate. Here we have to consider the two cases. That is nothing but the case number 1 is the upper surface get heated by a fluid, flowing fluid, or a lower surface get cooled by a flowing fluid. In that case, we have to use these two correlations for the laminar flow and turbulent flow. So in this case, the flow is considered to be laminar flow if the Rayleigh number is in between 10 raised to 5 to 2 into 10 raised to 7. At that time, the Nusselt number or average Nusselt number can be written as 0. Or average number, the correlation for natural convection can be given as the average Nusselt number is equal to 0.54 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 4. And if the product of Grashoff's number and Prandtl number is greater than 2 into 10 raised to 7 and less than 3 into 10 raised to 10, then the flow is considered to be turbulent flow. In that case, the empirical relations for natural convection can be written as average Nusselt number is equal to 0.14 into bracket GR multiplied by PR raised to 1 by 3. This is the first case. The case number second is the lower surface get heated because of a flowing fluid or upper surface get cooled because of flowing fluid. In that case, we have to use these two correlations for the laminar flow and turbulent flow. So in this case, the flow is considered to be laminar flow if the product of Grashoff's number and Prandtl number is in between 3 into 10 raised to 5 to 3 into 10 raised to 10. So in that case, we have to use the correlation average Nusselt number is equal to 0.27 into bracket GR multiplied by PR raised to 1 by 4. And the product of Grashoff's number and Prandtl number is greater than 7 into 10 raised to 6 and less than 11 into 10 raised to 10. Then that flow will be considered as a turbulent flow. In that case, we have to use the correlation. The average Nusselt number is equal to 0.107 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 3. Now, for the horizontal cylinders, Adams has recommended the equations for the laminar flow and the turbulent flow. Now here, if the product of Grashoff's number and Prandtl number is in between 10 raised to 4 to 10 raised to 9, then the flow should be considered as a laminar flow. In that case, the average Nusselt number can be written as average Nusselt number is equal to 0.53 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 4. And the product of Grashoff's number and Prandtl number is greater than 10 raised to 9 and less than 10 raised to 12, then that flow will be considered as a turbulent flow. Then the average Nusselt number can be written as average Nusselt number is equal to 0.13 into bracket Grashoff's number multiplied by Prandtl number raised to 1 by 3. Now, the Churchill also provided the correlation for horizontal cylinder. So here, this relation we can use in between 10 raised to minus 5 to 10 raised to 12. The product should be in between 10 raised to minus 5 to 10 raised to 12. So this is the wide range of the product of Grashoff's number and Prandtl number. So over the wide range, we can use the Churchill and Chu equation. So by using this, Churchill recommended the equation for the average Nusselt number as equal to, in a square bracket, 0.60 plus 0.387 multiplied by Grashoff's number multiplied by Prandtl number raised to 1 by 6, in a curly bracket 1 plus in a bracket 0.559 divided by PR bracket complete raised to 9 divided by 16 curly bracket complete raised to 8 by 27 square bracket complete. Now for the horizontal cylinder, the outside diameter is used as a characteristic dimension. Now next point in this lecture we have to cover, that is nothing but combined free and forced convection. In many cases, if the flowing fluid is having very less velocity, then we can see or we can analyze the heat transfer by convection, that is the combination of free and forced convection. Okay, so in some cases the force and free convection are combinedly dominating to transfer the heat from the surface to the fluid or fluid to the surface. So we have to analyze whether the heat is transforming by forced convection or a free convection or combination of free convection and a forced convection. So for that purpose, we have to take the help of a Grashoff's number and a Reynolds number, because the Grashoff's number is dealing with natural convection, whereas the Reynolds number is dealing with the forced convection. Now, on the basis of these two numbers, we can segregate whether the flow the heat transformation is happening because of the natural convection or forced convection or combination of natural and forced convection. Now here we go. If the free convection effects are negligible when the Grashoff's number is very less than Reynolds number square, and if we consider that free convection dominates over the forced convection when Grashoff's number value is very higher than the Reynolds number square. In certain situations where the free as well as forced convection are comparable magnitude, so the dimensionless group GR divided by Reynolds square, that is not Grashoff's number divided by Reynolds number square, is used to deal with the convection regimes. If the Grashoff's number divided by Reynolds number square is greater than 1, then the heat transfer will be considered as a purely free convection heat transfer. If this Grashoff's number divided by Reynolds number square value is nearly equal to 1 or equal to 1, then it will be considered as a mixed free and forced convection. If this Grashoff's number value, Grashoff's number divided by Reynolds number square value is very less than 1, then we have to consider the forced convection or a pure forced convection. Now, in the mixed convection regimes, the Nusselt number is calculated by using following equation. So, Nusselt number raised to m is equal to Nusselt number for a free convection raised to m plus or minus Nusselt number for forced convection raised to m. Now here we have to add or subtract the Nusselt numbers which are getting from a free convection or a forced convection. Okay, so the positive or negative sign is taken if the free convection flow occurs in the same direction of a forced convection. That is nothing but the positive sign is taken when if both the convection directions are same. That is nothing but forced convection direction is the same as that of a free convection. The negative sign is taken if the free convection flow occurs in opposite direction to that of forced convection. Generally recommended value of m is 3. So this m value generally recommended as a 3. Now this mixed convection correlation we have to check out for the external flows and internal flows. So in external flows we have considering as a vertical plate or a horizontal plate, or flow over a vertical plate or a horizontal plate. So in case of external flow, the local Nusselt number for a mixed convection on a vertical plate is given as local Nusselt number is equal to 0.508 Prandtl number raised to 1 by 2 multiply by in a bracket 0.952 plus Prandtl number raised to minus 1 by 4 multiply by gr suffix x, that is local Grashoff's number raised to 1 by 4. And we have to use this formula or the correlation if local Grashoff's number divided by local Reynolds number square is less than or equal to 1. Now if this value is greater than 1, then we have to use the equation local Nusselt number is equal to 0.332 multiply by Reynolds number raised to local Reynolds number raised to 1 by 2 Prandtl number raised to 1 by 3. That is nothing but this equation is used for the forced convection only. So for horizontal plates, if the Grashoff's number, local Grashoff's number divided by local Reynolds number raised to 2.5 value is very less than 0.83, then the following equation for forced convection may be used. Then simple forced convection equation we have seen for the local Nusselt number, that is nothing but local Nusselt number is equal to 0.332 local Reynolds number raised to 1 by 2 Prandtl number raised to 1 by 3. Then the internal flows, for the internal flows and for the mixed convection in laminar flows, Brown and Govin recommended a correlation of the form. So Brown and Govin has given the equation. So according to recommendation, the equation is average Nusselt number is equal to 1.75 into bracket mu b divided by mu s raised to 0.14 in a square bracket gz plus 0.012 in a bracket gz multiplied by gr raised to 1 by 3 rest bracket complete raised to 4 by 3 square bracket complete raised to 1 by 3, where this gz is a Gray's number given as product of Reynolds number multiplied by Prandtl number multiplied by d by L, and where mu b and mu s are the viscosities of the fluid at the bulk mean temperature and the surface temperature respectively. Now for this particular mixed convection with turbulent flow in a horizontal tube, Metai and Eckert suggested the equation. So according to this, for a turbulent flow, Nusselt number, average Nusselt number can be written as 4.69 multiplied by Reynolds number raised to 0.27, Prandtl number raised to 0.21, Grashoff's number raised to 0.07 multiplied by d by L raised to 0.36. Okay, thank you.